So before anything else, let me introduce to the topical workbook for Computer Science 2210 or 0478. This is the workbook 1 for paper 1, basically computer systems. And as you can see from the table of contents, I've included questions on each and every subtopic from the syllabus along with the mark scheme. And these are some of the actual questions, actual pages as a preview from the workbook. Section 1.1, 1.3, 2.2, 3.2, 5.3 cybersecurity and artificial intelligence. This is just to show you a glimpse of what type of questions are included in the workbook. There are many more questions where these come from, and around 18 to 20 questions on an average are included for each and every topic. A must buy if you want to boost your grade. Similar to the paper 1 workbook, I have designed a paper workbook for paper 2 as well. This is for algorithm, programming and logic for CIEs either 2210 or 0478 GCE or IGCSE Computer Science. As you can see, it contains questions on every subsection of the syllabus content for paper 2 along with the mark scheme, so you can understand each and every question, each and every algorithm. These are some of the few pages from the workbook just to give you a glimpse of what type of questions are included. As you can see, this is 7.1, this is 7.7, 8.3 and section 10 Boolean logic. So a lot more questions are included in the workbook. A must buy if you want to have a very good score in your Cambridge examination. Order now. Assalamu alaikum warahmatullahi wabarakatuh. Welcome to another physics lecture. So we were discussing section 3 waves, and we were specifically on section 3.2, that is light, and today we are going to start our discussion from where we left it off, and we are going to start discussing lenses. Now lenses would more or less always be defined using a lens diagram, and in physics a lens diagram always have three things: a principal axis, a principal focus or focal point, and focal length. The principal axis is the line which passes through the center of the lens, whereas the focal point is the point at which rays of light traveling parallel to principal axis converge and intersect each other. And focal length is the distance between the center of the lens and the principal focus. Here's a diagram to make you understand. Basically, this is the principal axis, a ray of light that travels from the center of the lens, and the point at which all of the rays of light passing through a lens and then converging or intersecting with each other is known as the principal focus, whereas the distance between principal focus and the lens, or specifically the center of the lens itself, is known as the focal length. Now there are two types of lenses, and what exactly is a lens? It is a piece of equipment, a piece of glass that forms an image by refracting light. There are two types of lenses: converging lens or convex lens, and diverging lens or concave lens. In a converging lens, parallel rays of light are brought to a focus and they are bent so they intersect with each other. The point is called the principal focus, and this lens is known as a convex lens. The distance from the lens to principal focus is the focal length. This depends on how curved the lens is. The more curved the lens, the shorter the focal length. If this lens, the more curved this lens would be, the shorter would be the focal length. Now what is a diverging lens? In a diverging lens, rays of light are made to diverge or spread out from the lens or from a point. The lens is also known as concave lens. The principal focus is now the point from which the rays appear to diverge from. As you can see, in In a concave lens, the point from which the rays of light diverge out from, that is known as the focal the principal focus, and this would be the focal length, whereas this is the principal axis. How do we represent lenses? By drawing diagrams like these. For a converging lens we draw it like this, for a diverging lens we draw it like this. Now there are two types of images that are formed by a lens: a real image and a virtual image. A real image is an image that is formed when a light ray converges and when different light rays converges and meet each other, and this can be projected onto a screen. A real image is one produced by the convergence of lights toward a focus. Real images are always inverted, and they can be projected onto pieces of paper or screen. An example of a real image is the image formed on a cinema screen. Real images are where two solid lines cross in a ray diagram. A virtual image is one that is formed when light rays from an object do not meet but appear to meet behind the lens. These images cannot be produced onto a screen. It is formed by the divergence of light away from a point. They are always upright. They are never inverted. Virtual images are never inverted. Virtual images cannot be projected, and an example of virtual image is a person's reflection in a mirror. Virtual images are where two dashed lines or one dashed and one solid line cross in a ray diagram. Now when talking about converging lenses produce real images. They can be used to form images of objects placed in front of them. The location and nature of image can be found by using a ray diagram. Depending upon the size between the object and the lens, different type of images can be formed. And how do we complete this ray diagram? Basically, we draw a parallel line from the top of the object towards the center of the lens. From that point, once it hits the center of the lens, we converge it towards the principal axis and we extrapolate that line. We draw the second line from the top of object and in a way that it must cross the center of the lens and continue on. The point at which the two lines intersect is where the object's image would be formed. The above diagram shows that the image is formed when the object is placed at a distance between one focal length and two focal length from the lens. As you can see, this is the focal length and this is twice the focal length, and currently the object is in between 1f and 2f, means between focal length and twice the focal length. In this case, the image is real. The image is enlarged. As you can see, it has more height. The image has more height than the object, and the image is inverted because this is a real image. The following diagram shows what happens when the object is more distanced, means it is more than 2f apart from the lens. In this case, the image is inverted, the image is diminished or smaller, and it is real. The image would be formed as slightly before the 2f mark on the right hand side. If the image is placed at exactly 2f, then what happens? The image is real, the image is inverted, and it is the same size as the image, and it is formed on the other side of the lens, exactly 2f at a distance of 2f. We can use converging lens to form virtual image as well. a converging lens will produce a real image of an object which is placed at a distance greater than the focal length from the lens. If the object is placed closer to the lens than the focal length, means if the object is placed before the focal length, then a virtual image will be formed and the converging lens ray diagram will be drawn in this way. Here is the object. We draw two lines. One will be parallel to this principal axis, and once it hit the center of the lens, we draw a line like this, and the other would pass through the center of the lens, and at this position the eye would be placed, and we are going to extrapolate these two lines in form of dashes or to show virtual lines, and at the point where these two dashes meet where an upright image that would be magnified will be created. A virtual image is formed when object is placed closer than the focal length, and we have just discussed how to draw this line. We simply draw the ray diagram and then we extrapolate their virtual lines, and the point at which they meet, image would be formed. In this case, the image is virtual, the image is magnified, and the image is upright. Next we have diverging lenses, and they produce virtual images. They can also be used to form images. If an object is placed further from the lens than the focal length f, then a diverging lens ray diagram will be drawn like this. In a diverging lens, this would be the eye. Eye cannot be over here, as focal length is before the focal length is always or the focal point is always before the diverging lens. Now if we have placed an object after the focal point, image would be formed like this. Here is the f, the focal length, and over here the image is formed. Start by drawing a ray going from the top of the object through the center of the lens like this, and another ray would be drawn straight and then it would be diverged out. This ray would be extrapolated in form of a dashed line. At the point at which this dashed line and this second line meet would be where image would be formed. In this case, the image is virtual, the image is diminished, and the image is upright. Comparing converging and diverging lenses, the image produced by a converging lens can be either real or virtual. That means it can either be inverted or upright. The image produced by a diverging lens is always upright or always virtual. Magnifying glasses. If the object is placed closer to the lens than the focal length, the emerging rays diverge and a real image is no longer formed. Instead, a virtual image is formed that is enlarged or magnified. When viewed from the right hand side, the emerging rays appear to come from a point on the left. This point can be found by extending the rays backward or creating virtual rays. A virtual image would be seen that would be virtual, enlarged, and upright. And using a lens in this way allows it to act as a magnifying glass. Also remember the formula for linear magnification: image length divided by object length. Converging and diverging lenses are commonly used in glasses to correct defects of sight. Converging lenses can be used to correct long-sightedness, and diverging lenses can be used to correct short-sightedness. What is short-sightedness? People who are short-sightedness have eyes that are too large. Basically it means that they cannot see things that are far away and only see things that are closer to them. This is because the eye refracts the light and brings it to a focus before it reaches the retina, hence the retina is not able to process the light signals. This can be corrected by using a concave or a diverging lens in front of the eyes. Whereas somebody who's having long-sightedness, they have smaller eyes. That means they cannot clearly see things that are closer to them, because the lenses in their eyes refract the light, and they are brought to a focus beyond the retina and on the back side of the retina, hence they are not able to see things that are close to them. So for correcting long-sightedness, convex lenses are used so that they converge the light rays exactly onto the retina. Example question: the diagram shows a thin converging lens of focal length f. Where must an object be placed to produce a real image in the position shows? This is the position of image. Now let's find out. If we have to now one of you can say one of the rays from the between object and image should be passing through the center of the lens. So we draw it like this. The other one should converge at around f, and it would hit the center of the lens, and from that position it will be parallel. Let me draw it a bit correctly. Okay, the other image should be the other ray should pass through the focal length point, and then it would be straight parallel to the principal axis. And as you can see, the point at these two rays meet is near to A. Now obviously this is, I've just drawn the diagram randomly, but it gives us a closer idea that A should be the point at which our two rays would meet, so A should be our answer. An object is placed in front of a converging lens of focal length 4 centimeter. The height of the image formed is 6 centimeter. This is the image. The arrangement is shown on the scale diagram. So over here, one complete block and half represents 6 centimeters, whereas this is the height of the object. What is the linear magnification? Now formula for linear magnification is supposed to be image the height, or you can say the length of image divided by object length. Now we know the length of image is 6. Let's find out from the graph the height of the object. So as you can see, this is 5, 6 and 7 small boxes. That would be something like that is roughly the half of this. So this is 6, and that means this must be 3. So 6 divided by 3 is 2, and that means C would be our correct answer. Dispersion of light. White light is a mixture of all colors of the spectrum. Each color has a different wavelength, making up a very narrow part of the electromagnetic spectrum. White light may be spread into its all colors by passing it through a prism. This is done by refraction. Violet light is refracted the most, while red light is refracted the least because of their frequencies and wavelength. This splits up the colors to form a spectrum or a rainbow. This process is similar to how rainbow is created in the clouds. Now you should know this diagram very well. When white light hits a prism, it is refracted like this, and when it goes out from the prism, the top color is red, whereas the most bent one is violet. So you can learn these color in form of an acronym as well, Webb-Gear or Roy G. Biv, however you want to learn it. From the bottom, violet, indigo, blue, green, yellow, orange, red, a web gear. The visible light is defined as the range of wavelengths which are visible to humans. Visible light is only the part of the electromagnetic spectrum that is detectable by human eyes. It only makes up 0.0035% of the whole spectrum. In the natural world, many animals are able to perceive beyond visible light and can see infrared or ultraviolet rays. The different colors of waves correspond to different wavelengths. Red has the longest wavelength and the smallest frequency. Violet has the shortest wavelength and the highest frequency and energy. Light is a transverse wave. The different colors of light all have different wavelengths and frequencies. So this is basically the same thing. Light of a single wavelength or a single color is also known as monochromatic. This is our image to show you different wavelengths and frequencies of different colors of light. Violet has the, this is the wavelength. Violet has the smallest, 400 nanometers, then indigo, then blue, then green, then yellow, and then orange, and then red has 665 nanometers. Whereas the frequency for violet is highest, whereas the frequency for red is lowest. Example question: white light enters a prism and forms a spectrum. The rays in the air are labeled. Which diagram shows how the white light is spread? So from the bottom color is supposed to be violet and the top color is red, but our answer over here is not A, as this diagram shows that the light splits into its constituent colors out on the other edge of the prism and not when it strikes the prism itself. Hence this diagram is wrong. This diagram is also wrong over here. The color combination is also wrong. This diagram is correct, as it shows that as soon as the light strikes the prism, it has started to refract, and then when it goes out the prism, it is in the correct order from red till violet. So our answer would be C. That is it for today. I hope you have understood everything. Please do give your comments and let me know if you have any problems. I'll see you guys in the next lecture. Take care. Allah Hafiz.